Okay, we're back. So the third section in this chapter here, we did languages and grammars, and now the third section is graphs, and it's just as straightforward as we're trying to establish so that everybody is using the same vocabulary and everybody is sort of using the same symbols, and basically all on the same page. So some very straightforward, but mostly vocabulary work for today. So let's have a look here. Let's say bring that back and slide it over. There we go. Okay, so most of this, I expect, it's been my experience from talking to people in the past who've taken the class, most of this will be straightforward, just simply vocabulary. So just as an example here, the nodes or vertices, you could use N or V, and I happen to use N, so just want to make sure everybody's on the same page. Okay, so a simple graph, and of course there's an example of it right here below. A simple graph is a collection of nodes and edges, and is a finite set of vertices or nodes. I usually call them vertices, and E is a set of edges, and each edge is a set of two distinct vertices. So here's the simple example here. It has 5 vertices, so I call them with V's, and the edges, for example, this edge right here, has connects V0 to V2, and it's a set so that there we go. It's a set so that that means that there's no, it doesn't like go from V0 to V2 or from V2 to V0. It's a set, so you can put either one first and either one second. Okay, so that's the point of a set. So each edge is a set of 2 distinct vertices, so you can't have a loop in the definition of simple graph. Just as a matter of convention is that instead of writing the set V comma V hat, we usually just write E as VV hat. And that's awkward because sets are unordered. So we could write the same edge as V hat V, but it's really a big time saver. It saves a lot of effort, so we're going to live with the awkwardness. Now there are lots and lots of variations on this theorem. On this definition. Lots and lots of variations used for different modeling circumstances that a simple graph can't model. And one variant that allows some vertices to connect to themselves. So you could have a variant of that definition where you're allowed to connect a vertex to itself. I mean, if you think of this as a map with some cities, well, of course there are some roads that go only within this city. So that's a loop. Another example would be a multigraph where you can have more than one connection between two edges. Here I've got 3 different connections between V2 and V4. And again, if you imagine it's a map, you can easily see that there are 3 bridges between these 2 cities or whatever is the meaning of the connection. So very common is a weighted graph where these edges have some weights. I mean, you might have, for example, a 6 there and a 4 there. And what that might mean is that it takes you 6 minutes to drive from V3 to V4, or that it takes you 4 minutes to drive from V3 to V2. So that could happen. And each of those numbers is called the weight, and maybe it's the time it takes or the money that it costs or something like that. Okay, so that's the basic definitions for members of a graph, and so I want to talk about some words about paths. So 2 graph edges are adjacent if they share a vertex. So that 2 graph edges are adjacent if they look something like UV and VU. It's going to be UV and VW. So, for example, here's UV and here's VW. Having a little trouble locating. There we go. There's VW. So they share the V. A walk is a sequence of adjacent edges. So V0, V1, V1, V2, etc. You see that the first two share the V1. The second 2 are going to share the V2, and etc. And then the length is just simply the number of edges. If the initial vertex V0 equals the final vertex, then you might say it's a closed walk, otherwise it's an open walk. If no edge occurs twice, then it's a trail. These are some of these words are more obscure than others of these words. If the vertices are distinct, except maybe that the initial vertex equals the final vertex, that it's a path, so no vertex occurs twice then if a closed path with at least one edge is a cycle, and finally a graph is connected if between any two vertices there's a path. So a lot of vocabulary words. Some of them we'll use more often than others, and frankly some of them it's not really perfectly clear that everybody in the world uses that word. But the idea is that we often want to move around in the graph, and so we have some vocabulary words to express that we can move around in the graph. The adjacency matrix for a graph G is a matrix representing that the graph has entries that equal the number of edges that from Vi to Vj. So I want to go back to the graph on the previous slide and draw down a matrix. So see how I do here. There we go. I'm drawing I lost it. Darn it all. There we go. So I'm drawing a matrix. And here I see that there is an edge from V0 to V1. There's no edge from V0 to V0, but there is an edge from V0 to V1. And likewise, there's an edge from V1 to V0. What's the story with V0 and V2? Yes, and likewise V2, V0. And what's the story with V0, V3? No. V0, V4? No. And like that. And so you're building up a collection here of entries in a matrix that represent whether there are edges. Sometimes you might want to have just the 1 and 0, but sometimes you might want to have, if for example there is 3 edges from V0 to V2, why then you write a 3 here. Okay, so what you're trying to do is represent the graph in some reasonably efficient way. It doesn't have to be the most efficient way for the purpose that we're trying to get through, but some reasonably efficient way to represent what's in the graph in a computer. How do you represent this stuff in a computer? Okay, so the adjacency matrix representing the graph has an ij entry that equals the number of edges from Vi to Vj. And the major point for our purpose of the adjacency matrix is that if you have an adjacency matrix and you look at m squared, then the entry is the number of length 2 paths. So if there are 3 ways to get from V0 to V1 in 2 hops, then you'll have a 3 there. So matrix multiplication does what it should do. Matrix multiplication does the counting for you. If there are 5 ways to get from V0 to V7 in 2 hops, why then there will be a 5 there in m squared. Okay, and then another definition, maybe this should have gone on a separate page because it's a separate topic as opposed to the adjacency matrix, but another definition. A k-coloring of a graph is a partition of the vertices into k many classes with the property that adjacent vertices don't come from the same class. So it's called a k-coloring because that's traditionally how you represent what's happening here. But it's a partition of the vertices into different categories with the property that you can't connect 2 red vertices, you can't connect 2 blue vertices, you can't connect 2 green vertices. And really, I think one example gives an idea of why I want a partition. So suppose we have computer science classes and we want to schedule final exams. Well, of course, you can't schedule final exams for 2 classes at the same time if they share a student. So we have all these classes. Classes have these elaborate names. So, for example, we have the first class is 1007, the second class is 3137, the third class is 3154, etc. So there are a bunch of CS classes. We see that class 1007 and class 3137 share a student. So they can't be scheduled for the same time. So you might color all of the classes that are going to be scheduled at 8 o'clock in the morning. You might color them blue. Well, you can't, one of these might be blue, but they can't both be blue. And likewise, 1007 here and 3157 can't both be colored the same color. They can't both be blue, they can't both be green, whatever color. So the idea of coloring is you got to break the vertices into different categories, and the categories happen to be called coloring, but don't worry about the name. The point is you want to have different categories, in this case because you want to schedule the final exams at different times of day or different days. So it's sensible to say, what's the minimum number of time slots to schedule the final exams for these classes? What's the minimum number of colors you can use to color the vertices? Okay. Then the last topic for the 3 slides for today, in section 3 of chapter 3 has 3 slides. So one way to express that two graphs are maybe not equal, but essentially the same. I had a professor who used to say that one is the other one colored green, which I always thought was a good way to express. The only changes are visual. The only changes are typographic. Two graphs, G and G hat, are isomorphic if there's a one-to-one and onto map from the nodes, from the vertices, so that the edges line up. The graph G has a vertex V1 VI VJ if and only if G hat has F of VI F of VJ. So again, you make a connection, you make a one-to-one and onto map between the vertices with a property that if there's an edge VI VJ in the graph G, then the edge F of VI F of VJ is an edge in G hat, and vice versa. If F of VI F of VJ is an edge in G hat, why then VI VJ is an edge in G. Okay, so we're trying to express that two graphs are somehow the same except for some visual or typographic differences. Showing that graphs are not isomorphic usually entails finding some graph theoretic pattern to them in which they differ. So the most common and useful property is to consider the degree of a vertex, which is the total number of edges touching that vertex. You got to be a little careful now. If you have a vertex and it's got some edges going out, okay, you count each of them. That's fine. That's 3. But if you have a loop, that's going to make a total of not 4, but a total of 5. Okay, so you have to count the number of connections here, and the total number of connections is 5. Anyway, that's a degree of a vertex. Then the degree sequence of a graph is a non-increasing sequence of degree vertices. So if, for example, I had a graph, if I had a graph with, it's got how about the most number of the vertex with the most highest degree is 5, and then 4, and then 3, and then 2, and then 1, and there are no isolated vertices. So maybe I have 3 vertices like that, and 2 vertices like that, and 4 vertices like that, and 1 vertex like that, and 2 vertices like that. I'm sorry, I'm not sure if that's a legal possibility, is why I'm hesitating. Then I would write down for the degree sequence 5, 5, 5, 4, 4, 3, 3, 3, 3, 2, 1, 1. And again, I'm sorry, I'm not sure if there actually is such a graph. I just made the example up. So if you have 3 vertices, so this is a degree, and this is number of vertices with that degree. If you happen to have 3 vertices of degree 5, then the degree sequence has a 5, 5, 5 in it. Okay. So if you find 2 graphs and they have different degree sequences, then they're not isomorphic. So that's the most common way to show that graphs are not isomorphic. To show that graphs are isomorphic, the most common thing is to show that is to actually produce the isomorphism. Give me a function, a connection between vertices of G and vertices of G hat that has the property in the definition. And I have to say that that's actually a hard problem, a quite hard problem. If you give me a graph with 5 vertices, well, I can usually eyeball the answer. But if you give me a graph with 500 vertices, that's a very hard problem. That's a problem that would be absolutely a research problem today. Okay, anyway, so most of what we've done today is vocabulary words about graphs and vertices and paths and all that kind of stuff. Just simply trying to make sure that everybody's on the same page, that everybody is using the same letter, capital G, for graphs and that kind of thing. Okay, all right, very good.